Okay, so this is the session on thermodynamics and statistical mechanics. So we've seen the classical mechanics, and this is more ideas that we have to put together than things that are completely done, but it gives you a sense of what pieces we're working on, and maybe you have ideas that we should be aware of. So quick recap of what we said before. The main goal of the project is identify a handful of physical starting points from which the basic laws can be derived. This means identify physical principles that are a starting point, but this physical principle at the end of the day will need to also recover the mathematical structure to be able to show that we have fully derived the theory. The underlying perspective is that what we are really interested is not just what really exists. We need the things to be experimentally accessible in a way that it's reliable so that we can actually make experiments, study things experimentally, and make correlation and write laws, because laws are about things that we can reliably study. And then the idea is that the physical theory themselves are not really the objects that are here, are most of the time idealized accounts. So understanding the role of this abstraction and idealization is important, because part of what you find in the theory is actually a sub-product of this idealization process. And part of what you find in the theory are requirements from studying things experimentally. So it's very important to us that we understand those constraints, because we do believe that those constraints end up in the physical theory, and so therefore you can't understand the physical theory if you don't understand these pieces. And this means that we not only have to look at the foundation of physics, but we also have to look at the foundation of mathematics to really understand what these tools are mathematically, how they're defined, and how exactly they map to the physics. And of course, we need a little bit of philosophy of the science, but only the part that allows us to fully understand what the boundaries are here, how does the idealization process work. We're not interested in this part of philosophy of science that look at sort of what really exists in a more ontological sense, because typically those things are not things that reach the empirical reality, which is about sort of only the regular parts of that. The underlying thought is that if physics is about creating models of empirical reality, then the foundations of physics should be a theory of models of empirical reality, so that we know how these models are constructed, what are their limitations, in the same way that in mathematics, the foundation of mathematics is proof theory, so that you know what the limitations of mathematics are there, you understand what it means to create proofs. And in computer science, it's really finding what things can be computed or cannot be computed. So this is more or less the same thing. And this gives us a different approach to the foundation of physics. We are not interested in constructing interpretation. We're not interested in understanding a theory of everything. What we're really interested in is understanding and creating a theory about physical model, find what are these general physical principles and requirements that are needed to construct physical models, and create a general mathematical framework such that every physical theory has to be a piece of an instantiation of this mathematical framework. And then the idea is that we find specific assumptions, and with the specific assumption, you recover the different theories in physics. We have two approaches. One is called reverse physics. We start with the physical laws that we already have and trying to tease out the smallest set of assumptions that are required, that are inside the theory, that are enough to fully describe it. And then we have another approach called physical mathematics that starts from scratch and layers out all the axiom, all the definition with a physical justification, such that the mathematics that we get, we are sure that it's there to capture and only capture physical qualities of the system. So this is the general spiel in 4 minutes. And for this session, we're going to talk about the reverse physics approach for thermodynamics and statistical mechanics. So first, I want to point out some puzzles that are there in thermodynamics related to the things that we generally talk. So for example, we say that entropy is disorder. And in fact, if you mix water and vinegar, you are going to get a more disordered state when you increase entropy. But when you mix water and oil and you put them together, and still in principle, you are increasing entropy, but you haven't increased disorder. So probably disorder is not a very good and intuitive characterization for entropy, and doesn't quite work. Another thing that we talk about in equilibria, where there's a general sense that there are two types of equilibria, dynamic and thermodynamic, and they don't seem to quite work in the same way. So if you imagine to have a damped harmonic oscillator, and this is position and this is momentum, this is going to circle, every trajectory is going to spiral to the center where it's you've lost all the energy and your oscillation has stopped. And the idea is that this is a dissipative force, and it shrink phase space volume. But a smaller volume means a smaller entropy. And therefore, we are saying that a dissipative force is reducing the entropy, which kind of don't make sense. We would expect the dissipative force to increase entropy. And here we have the opposite. Similarly, an equilibria in dynamical system is an attractor. The idea is that whatever equilibrium it is, it could be a point, could be a circle, the volume around it is going to shrink. And again, smaller volume, smaller entropy. And so we seem to be saying that entropy decreases as we go to equilibrium. And again, it doesn't quite make sense. So what's up with that? And another thing that is possible about entropy and equilibria is relativity. Because if we say that thermodynamic equilibrium is when we wait until nothing changes, and we put in the Newton's first law that a body remains in motion at constant speed, then we don't have equilibrium. Like the things keep moving, the position keeps changing. So that definition doesn't quite work. Or if I have a gas equilibrium in one reference frame where all the macroscopics stay the same, I can move, and now relative to me, the position is changing. So is it an equilibrium or not? Is it equilibrium for that guy and not for me? Or let's say that I have a gas that is increasing the temperature very slowly. So we basically can imagine it that it's always at equilibrium, right? But again, if I have a moving reference, the axis will cut this region in a different way. And now it's not going to see the same body at the same temperature. So it seems that an equilibrium is not an invariant property. Like what's up with that? How can we have equilibrium in the first place? Doesn't seem to be well defined. And other things when we talk about equilibria and information, we say, oh, equilibrium is related to information theory. So entropy can be seen as information, which is minus the integral of rho, where the rho is the distribution of the microstate. And I suppose you have a gas that it's an unknown temperature, which could be T1 or T0 with a 50% chance. Well, that encodes 1 bit. So we would expect the entropy of when I mix this thing of the entropy going up of 1 bit. But if you do the mixture, you take the two distribution and you put them together and you mix them. Since there is some overlap between the distribution of the gases, then this is strictly less than the increase of 1 bit of entropy. It decreases less of 1 bit of entropy. So that doesn't quite make sense. And say that entropy is really information, and where rho is the distribution of a macrostate. And now I forget that the temperature of what the temperature is of heat sources. So I increase my uncertainty, the entropy is higher, and now I can extract less energy from the heat source. That doesn't make sense. So the point is that there are a lot of things in thermodynamics that are sort of not quite there. Clearly, in some sense, entropy is about information. In some sense, entropy is about disorder. And the thermodynamic equilibrium is about things not changing. And equilibrium identifies a privileged equilibrium system. But the problem is exactly what sense these things are true, exactly why, what is the correct understanding of this. And to me, that's the fundamental problem in thermodynamics. That's everything is hodgepodge. Yeah, it kind of works like that. We never have crisp definitions of what these things are and why they are like that. And so to start putting some order in this, one of the first things that we did was to have a sort of a good characterization of information entropy, that it's sort of decoupled of physics because information is entropy is used in many different places, but that really gives us an idea of what this quantity is and what is measured. And so suppose we have this simple problem. We have sets, in this case, sets of shapes. And we can see that in this set, there is basically almost everything is a circle. There are only two things that are different. There are still a lot of circles, but proportionally, there are more things that are not circle. And here we see that things are a lot more changing. So the idea is that we want to have an indicator of, if I give you a set, if I give you a distribution of how much the elements are close to each other, or how much variability there is there in the elements. That's basically what we are asking. We have a set of things. How different are the things in the set from each other? And the cool thing is that if you ask for an indicator of variability, that it's a continuous function of pi and only of the pi. Therefore, we don't care that there are stars, circles, or cats and animals, or physical states. We only care about the distribution. And we want it to increase when the number of cases increases, so that there is a sense that the variability increases when there are more cases, when things are more diverse. And that it's a linear in the probability when you make composition. Then what happens is that the minus p log p, the Shannon entropy, is the only indicator of variability. It's the indicator of variability that satisfies those requirements. And the interesting thing is that this characterization works across discipline, because in things like ecology and sometimes economics, the Shannon entropy is actually used to characterize variability of species, variability of things. And so this is a very good characterization that sort of works across things. And the meaning of that variability will depend on what are the elements in the set. So, for example, if you actually have a statistical distribution, you have a bag with different objects inside, and you calculate the variability, then the Shannon entropy is going to be the variability of what is actually there, which is one thing, or something objective. If you have a probability distribution, because there could be many things, but there is actually only one, then the Shannon entropy applied to the probability distribution gives you the variability of what could be there, which is different for the probability of what is there. And then the Shannon entropy is used a lot in machine learning agents, like in Bayesian sort of settings. In that case, the distribution is not about probability, it's about credence, it's about what an agent thinks there is there. And then, of course, the variability is the variability of what one believes to be there. And this is one of the most confusing things, is that there is a lot of people that study the Shannon entropy as related to agents, and then they apply it to physics, and they still attach this interpretation of the credence distribution in physical system, where the physical system, the distribution may be really a statistical distribution or a probability distribution. And so you get the wrong interpretation. You don't differentiate between these things. And so if you have this thing in mind, that the variability is a general tool for any set of things, realize that set of things could be different things, then you're going to have no problem understanding what this thing is. And now there is the connection to the actual thing that we know about, the Shannon entropy, the bits of information. Well, it turns out that that same indicator of quantitativity, the number that it comes out, can be understood as quantifying the minimum number of yes or no questions required to identify an element. So you have a bag of things, you know the distribution. I pick one element, and now you have to guess what element I picked. And you can give me yes or no questions. You're going to create a strategy based on what's in the bag and what the distribution is. And the optimal strategy is going to reduce the number of questions to the expectation value, to an expected number of questions that is given by the Shannon entropy. So you can understand that. I have a bag of things. It could be a distribution of states. I pick one state. How many questions do you need to ask to be able to know what state I pick? It's the same thing. Another characterization of the Shannon entropy is you take a distribution and you take a sequence of elements with from that distribution. You're going to have a set of permutations based on how, what are the chances and the fraction that all the elements have to have in the distribution. Well, if you take an infinitely long sequence and you calculate all the permutation of all the objects in the sequence, well, then 1 over n, the logarithm of that number of permutation corresponds to the Shannon entropy. So you can understand the Shannon entropy as quantifying the number of permutations that you would have in an infinite sequence if you get an infinitely many elements from your band. And so more variability, of course, for a distribution of at equilibrium, because at equilibrium things are going to be at the maximum variability, are going to be the maximum fluctuation, and therefore you have this connection to the physical entropy when you're understanding the element that you have in your distribution as physical. So this is sort of one way that is completely decoupled from thermodynamics that you can kind of understand well and put it aside, but it's not physics. It's information. Information is not physics. There are some parts of physics that you can describe like this, but one of the things that information entropy does not require is that idea of invariance, that information has to be the same for all observers. And requiring this to be independent from observer is exactly what, for example, gives us the classical phase space of quantum mechanics. Therefore, physics has more constraint than just information entropy. So let's try to understand instead what could be a good characterization of entropy in general for dynamical systems. And now we're going to basically start completely from scratch. And well, let's go directly from here. And let's say that we have a state space for a physical system. So this could be points in phase space. You can think of quantum state space. You can think of probability distribution. It doesn't matter. You have a space, you have a system, and you have a bunch of states that the system could be in at a particular time. And then you basically say, okay, I'm going to have the same state space at each time, right? This is the present, this is the past, and the future. And then I will call an evolution a complete description of the system at all time. So if I told you what the system did at every moment in time, of course, that's the most amount of information that I can tell you about the system. That's a complete statement about the system. If I only tell you the state at a particular time, of course, I'm going to tell you this. And now the idea is that a physical process could be understood as a set of possible evolution. If I am in this state here, I'm not going to be able to be in this state at the next state. So you're going to have the physical process, whether it's Hamiltonian or whether it's statistical, it doesn't matter. It's going to tell you this evolution is possible and this evolution is not possible because there is a constraint, you're not conserving the energy, whatever you're doing, that evolution is not possible. And so a process defines a set of all possible evolutions. And the idea is that a description at each time corresponds to a set of possible evolutions. So if I knew that at time t I am in this state, and these are the only possible evolution allowed by the process, then I know that I am in one of these two evolutions. And the idea is that we suppose that we can count the number of evolutions for a particular state, so that we have a function that given a particular state, it gives us this number. So for this is 2, for this is 1, for this is 2, and so on. Of course, the full mathematical thing is going to be a little bit more complicated, but well, let's assume that it's just that. A number that is given when we give a state. Now, the idea is that already you see that this idea of giving a measure to evolution is connected to the idea of probability. Because if I want to say what is the probability that I find myself here, knowing that at time t I was here, then we just have to count all the evolution here. We have to count the evolutions that are here, that also are in here. So we count the evolution for which we are in both, and we divide by the number of evolutions that go through here. And that's, of course, is going to be a number from 0 to 1, because the maximum is when all of these are exactly this, and it's going to be 0 when none of the evolution goes through that system. So that already gives us an idea of probability, which is nice. Now we put an assumption and say that the process is deterministic, meaning that if I know the state at a time, that allows us to predict the state at all future time, right? And this is what essentially allows us to write a law of evolution. If I'm here, I'm going to be here, and if I'm here, I'm going to be here. And now what you note is that if the process is deterministic and is deterministic, then the evolution can never split, because if it's deterministic, all the evolution that go through here will have to go through the same state. But they can merge. You can have two different conditions that then they merge in the same number. And so what's happening is that if we go through an evolution and we go and look at all the evolution that passed through here, all the evolution that passed through here, all the evolution that passed through here, this number can only increase or stay the same because evolutions can never split and can only merge. In the same way, if we can define a process to be reversible, if knowing the state at a time allows us to reconstruct the state at a past time. It's the same thing, just mirror image. And in this case, the number of evolution, since the evolution can merge, can never merge, and it can only split because we're going the requirement in the opposite direction, then this number, the number of evolution per state, can never increase, can only stay the same or decrease. And so we already found, and of course, if we have a process that is deterministic and reversible, then the number of evolution has to remain the same. And so we already found with this simple reasoning a quantity that for a deterministic process can never decrease, and it's equal, it stays the same if the process is reversed. Now, entropy also has to do something interesting at equilibrium. Now, consider a process where a system reaches a final equilibrium. Well, what happens is that, and you assume that the equilibrium can be predicted from the initial state. So, okay, you have a bunch of different states. There's going to be some kind of evolution here, but at some point they are going to go to the equilibrium state, and they're going to remain where the equilibrium is. Now, at that point, when we are in equilibrium, the evolution cannot merge anymore, and therefore the number of evolutions per state has to remain the same. And so not only our quantity never decreases and is equally reversible, but it finds its maximum at an equilibrium. And this really starts sounding like an entropy. Another thing that we need to require from the entropy is what happens when you have composite systems. So when you're composing two systems, we have a certain number of states for one, a certain number of states for the other. The state space is the product. But the evolution in general are not the product. So for example, here there is a correlation. So we have only 3 possible evolution of the joint system. And these 3 possible evolution correspond to 3 distinct evolution in the individual system. And the total number of evolution is not the product because there are correlations. These things are not possible. If the systems are independent, instead, for any evolution of one system, we all have a corresponding, it doesn't constrain the evolution of the other system, so we have all the possible permutation. Therefore, the number of evolution on one of the total is the product of the number of evolution of the individual system. What we can do then instead of looking at the number of evolution, since the logarithm of the product is the sum of the logarithm of mu, and we want our entropy to be additive, then we consider the logarithm of the number of evolution. And now this is going to be additive for independent system, because in an independent system, the number of evolution is going to be the product and things are constant. So now if we define this process entropy as being the logarithm of the count of evolution, we find that it is additive over independent system. And since the logarithm is a monotonic function, then for a deterministic process, it's not going to be decreasing. It's going to be equal if it's reversible, and it's a maximized equilibrium. So this really seems like a very good candidate for entropy. And does it actually match with the definition of entropy that we have? Well, now let's see if we can recover the idea that the entropy is the logarithm of the count of microstates. Suppose we have a process that is deterministic and reversible at a microscale, right? Not at the macro scale, but at the microscale. Then at a microscale, states and evolution are one-to-one. For each state, I have one evolution. For each one evolution, I have a state because it's deterministic and reversible. Now, then the count of microstates equals the count of evolution. Therefore, the entropy is the logarithm of the count of microstates. So our process entropy recovers the fundamental postulate of statistical mechanics if we're restricting ourselves under the assumption that the evolution at a microstate is deterministic and reversible, which is quite often what's being done in classical statistical mechanics. So that's good. But we also have the other, and this also explains why shrinking of areas does not actually decrease the entropy, because what happens is that the entropy for us is the count of evolution. So the fact that the evolutions are shrinking in phase space, while the count of evolution is still the same. So we have actually evolution that are more concentrated in the states. So in terms of a density, the density of evolution per state is actually increasing. And so you actually have the entropy increase that you would expect when you have areas that are shrinking when you are in a non-deterministic and reversible scenario. Now, the other thing that we need to recover is the idea of information entropy, because this is what actually is being used in the other approach to statistical mechanics, the maximum entropy, when you take the distribution and maximize the entropy. And so how do we recover that? Well, suppose that a macrostate is a dynamical equilibrium of some microstates. So we have the microstates are fluctuating, but we consider this sort of a macroscale as a single scale. So the macrostate fluctuation can be characterized by a stable probability distribution of rho in each small delta t. So you have an equilibrium, you have small delta t, things are jiggling around, but they're jiggling around according to a distribution over microstates. Therefore, an evolution for the microstate is a dense sequence of infinitely many microstates. Like you can take, within that delta t, you take, let's say, all the rational numbers. You know where the system is at the rational numbers. There is only one continuous function that is going to connect that, and that's going to be one of the possible evolutions. The idea is that the macrostate measurements cannot be sensitive to permutation of the microstates. And so the possible evolution is really all the possible permutation, infinite permutation that you have in that very small delta t, assuming that you have this distribution of them. And as we saw before, the Shannon entropy counts all the possible permutation of an infinite sequence. And so it's counting all the possible fluctuation that the system would have that are consistent with the distribution of them. And so we can recover from our idea of process entropy, the logarithm of the count of the evolution. Here we would have the logarithm of the count of fluctuations, and we recover the Shannon entropy as the thermodynamic. So that works. And so the idea here is then that you should think of the macrostate in equilibrium as sort of as a tube, right, of evolution at a lower level. Lower level, you have things that go around, right? But all these things that go around, they're sort of in the same tube. And then that tube is like your macrostate. And so an equilibrium means that no evolution enters or exits the tube. Everything stays inside. So external agents and external interaction have equilibrated. And the variables describing the macrostate can still change. So you still have things that move around. And you study this tube as it were a single line. From the distance, this tube is small enough, and I pretend that it's a single line, and that's what my macrostate is. So in this sense, the equilibrium is really when the evolution is decoupled from the environment and the internal dynamics. It's doing its own things, but it stays, it stays in its place, and I can study it as a bit. And this notion of equilibrium is automatically relativistic because it's group of evolution, it's group of timelines. And it also explains why quasi-static evolution is not relativistic, because depending how you cut, you're going to have a different count of evolution and different statistics. So that sort of makes sense. So the point is that we have defined a notion of entropy, sort of seemingly out of nowhere. We have not mentioned uncertainty, disorder, statistical distribution, information, lack of information. Therefore, these concepts are not fundamental, but you can see how they're related because, the more fluctuation, the more possible evolution, the more uncertainty you have, the more information you would have to pay to tell me to pick the actual evolution and so on. We have not discussed what type of system or state we have. It could be classical quantum biology. It doesn't really matter. And this sort of justifies why these techniques are used in areas that are not physics. And the process entropy increase is explained just by the definition of the setting. There is no mechanism. It's just if I have a system that follows that with these properties, I will have this quantity anyways. And now you would ask, okay, how does the process entropy become the entropy of a state variable exactly? Because we haven't really defined exactly, we have defined the process in terms of the entropy in terms of a particular process, but the same state can be used in multiple different processes. So how do we get one value of the entropy for the state? Well, The point is that what we really want to do is, in physics, is be able to mix and match different processes. So I start with one process, and then I put another process, start with a preparation, then I make it evolve, and then I put some measurement at the end. And so we really want to switch and mix and match like Legos, all these processes. And we need to put something at the junction. And the thing is that the evolution count needs to be the same at the junction, because we need to put things together such that we can make processes that are all together. And so when we put in the number of evolution, when we put these tubes together, they kind of have to match. Otherwise, it's not going to work. So the evolution count is a necessary feature of a theory for states and processes, because we want to be able to do this. And the idea is that equilibria can be assigned a unique entropy, because if I know that X is an equilibrium of A and B, then the number of evolution that I put here are going to be the number of evolution that I put here, which are going to be the same number of evolution that I put here, which means that it's the same number of possible evolution coming in that gives me X, which is the same number of possible that A has to give me X. So the kind of evolution must be process independence if we're really talking about equilibria, and these are the same equilibria for the different processes. So that's why equilibria are important, because they allow us to assign a unique maximal entropy to state. If we don't have equilibria, it's not clear what entropy we assign, because it depends from the process. And composite systems are also important because they're what allows us to decouple one system from the other. And it's a system independence is really what assigns us to an X maximum entropy to compensate. So the idea is that we can talk about physical objects as being different physical objects only if we find, at least in some cases, some processes where the evolution one is decoupled from the other. I can talk about a chair and a table, because in some cases, if I move the chair, the table stays there, it doesn't do anything. If every time that I move the chair, the table would move, then I really wouldn't be talking about a chair and a table independently. I would be talking about a joint system. Okay, so we can have a state entropy. We can assign a unique maximal entropy to states of independent equilibria. And given a set of states of equilibrium, we can define a function, and that returns a state entropy for each equilibrium. We can call this an equation of state of entropic forms. And so we have a goal reached here. And after a very general definition, we have found a simple notion of entropy, the logarithmic count of evolution, that has a fundamental Mostrian link to reversibility. And so we have found these things. We found that if we want to be able to stitch together different preparation and evolution, then we must define a count of evolution. The logarithmic count of evolution recovers property of the entropies, and equilibria are really what allows us to have things that are decoupled from environment and internal dynamics. And so all these ideas are nice. What needs to be done is to actually write down the full theory. Like, these are nice ideas, but we haven't yet developed all the mathematical machinery to do this, mainly because we got distracted by developing the machinery of other things. So we believe this is done. Of course, it needs to be done and ensure that it works. Now, we haven't talked about thermodynamics yet. And so how do we get to thermodynamics itself? Well, one of the things that we really need in thermodynamics that sort of extends this notion of equilibrium is that in thermodynamics, it's like you put things together, you remove a wall, you let them evolve and see what equilibrium they have, then you put the barrier again and you separate. And so there's always this idea of you're putting things together, let them do something, they reach an equilibrium and they put them together. And so what I really want to do here is the idea is that I have a joint system, and I take the state of one and state to the other. And of course, now the fact that this is an equilibrium does not necessarily mean that this is an equilibrium by itself and this is an equilibrium by itself. There could still be correlation. Therefore, this could be not an equilibrium, this is not an equilibrium. So we need to extend the notion of equilibria, not just to the whole, but of the definition of parts. And so this is going to be the idea of a thermodynamic process and a thermodynamic equilibrium, is the fact that not just the whole is an equilibrium, but all the parts are also at equilibrium and they are independent such that the entropy is out. And this is basically what needs to be sort of finalized to get here. And so a thermodynamic equilibrium you can really think as a sort of a descending order, like if I have this whole, this is in equilibrium, this is in equilibrium, this is in equilibrium, all these elements are in different equilibrium, and two systems that are in thermodynamic equilibrium are in thermodynamic if they're part of the same thermodynamic equilibrium. So this and this are in thermodynamic equilibrium because this whole thing is in thermodynamic equilibrium. And now, with this definition of thermodynamic equilibrium, where not only the whole is in equilibrium, all the parts in equilibrium, you can recover the zeroth law of thermodynamics that tells you that thermodynamic equilibrium is transit. Because if you say that X is in equilibrium with Y, and Y is in equilibrium with X, then it means that all these objects are part of the same thermodynamic equilibrium. Therefore, X and Z are part of the same thermodynamic equilibrium, and they must be in equilibrium themselves. And so if X is equilibrium with Y, and Y is equilibrium with Z, then Z is also in thermodynamic equilibrium with X. And so that's one of the things that we recover. To recover the other thing, then we just basically say that A is a thermodynamic system if the state space is formed by states of equilibrium or thermodynamic equilibrium. All the state variables are extensive property of the system. And this is something that we might actually be able to recover. There are some hints that we should be able to actually show that if all the states are thermodynamic states or thermodynamic equilibrium, or we can find a set of extensive properties. We haven't done that yet, but it probably can be done because we've seen other people do similar things. And then the important thing that one of these quantities is called the internal energy, and it's conserved under all thermodynamic processes. This is the only other requirement. And we indicate U with internal energy and Xi as variable variable. Ideally, we should be able to recover the existence of the internal energy by the work that we've done in classical mechanics, meaning that it should be a requirement of the deterministic reversibility at a smaller scale. But again, it's something that we haven't done quite yet. So under those assumptions, because the states are equilibria, then we have a function that for each equilibria gives us an entropy that is independent of the process. And because U and Xi are variable, we can express that entropy as a function of the variables, and this gives us an equation of state in entropic form. Once you have the equation of state in entropic form, there is a standard way to recover all the intensive variable by looking at the derivative of the entropy with respect to the extensive variable. The most important one is going to be the beta, which is the derivative of entropy with respect to energy. And this is the inverse of the temperature. And once you have these definitions and you put them together, you recover your usual thermodynamic expressions. And now that we have this, and now that we have this idea, what we really want to look at, since energy is one of the most important quantities, we want to study how changes in energy and changes in entropy relate to each other. And to do that, we define two essentially orthogonal direction in which you can exchange energy with our system. One, we are looking at changes of energy at equal entropy. So you change the energy, but the entropy does not change. And then we want to look at changes of energy at maximum entropy changes. And to look for that, we define two types of special system. One is called a reservoir. And a reservoir is going to be a thermodynamic system where the energy is the only state variable. So there's nothing else. And therefore, all the change is given by our beta. And we're going to assume that the beta is a constant. So essentially, a reservoir is something where that only has a temperature, a fixed temperature, and you only can exchange energy by increasing or decreasing the entropy. And you define heat as minus the energy lost by the reservoir during that transition. And so heat is just the energy exchanged under a purely entropic change. There is nothing else that is changing, only the entropy. There are no other extensive quantities. And now you have the dual. You want to define a mechanical system as a system such that the entropy is always the same for all the states. So whatever U and Xi you pick, then the entropy is constant. And the work is the energy acquired by a purely mechanical system during that transition. Now, in this case, when you make a transition, the change of entropy is always zero because the entropy is constant. And then what you can do is express your change of entropy as a change on the other variable. So effectively, by assuming this, you're assuming that the work is energy exchanged at a constant entropy. And since the entropy is constant, the energy is effectively stored in these other variables, because that's the only thing that you do. You put energy in, you're changing some of these variables, and then you can take energy out, and you take other values. One of the things that you note is that since the entropy is constant, right, you can kind of think as, let's leave that out. Let's continue. The first law. So you recover the first law since because the energy, as we saw, is constant. And since it's an additive, an extensive quantity, the difference in energy is going to be the sum of the different contribution. And one of the contribution is going to be the heat. The other one is going to be work. The other one is the change of energy of the system. And so you simplify the delta U is equal to Q minus V. And that's it. For the second law, we know what the entropy is because the entropy, again, is that logarithm and so on. And we know that the entropy cannot decrease because we proved it. And so we have the zero is it's less than the entropy change. And the entropy change, again, at the end of the process, so these are going to be independent. So the entropy is additive. And the change of entropy for the mechanical system is zero. The change of entropy for the reservoir is just beta times the change of energy of the reservoir. And therefore, this delta U, we saw that it was the heat. The beta is 1 over KB TR. We have, we just put this piece on the other side, and we just have that KB delta S is greater than Q over TR, which recovers the second law. So this seems to work. Now what we need is the third law. And if you recall our definition of state entropy, it's the logarithm of the counted evolution. And the idea is that the list that we can have is a single evolution, less than having an evolution, a state that goes through fewer than one evolution doesn't quite make sense. And therefore, the entropy should be greater or equal to the local logarithm of 1, which is 0. And so the state entropy is non-negative and it bounded from below from 0. And this recovers part of the third law. And we have to show that this is actually reached at the lowest energy. And to get that, what we can show is that the existence of equilibrium will force has to be concave. And since SU is non-negative, we have 3 cases. It can go like this, it can go like this, or it can go like this. So basically, it can go to infinity on one side, it can go to infinity on the other side, or never go to infinity. It's basically be concave like this. Remember, the entropy has to be greater than 0, so it cannot go below the axis. And so the first 2 cases can't but exist. You can't have 2 systems that one have the entropy at inside here and the entropy that goes to infinity on the other side, because you're not going to have an equilibrium like that. And so you can have that maximum have, let's say, C and A or C and B. By convention, we say that we have C and A, that is that the entropy is always going to go to plus infinity when U goes to infinity. And then basically this shows that the minimum entry is reached at the lowest energy state. So this recovers the full third law of thermodynamics. We're happy, but we can also make other arguments for why the entropy minimum entropy has to be 0. One of the things that we said is that the entropy is added for independent system. So F of the composite system A and B has to be equal to the sum of the entropy. We can have a null state or a null system, a system that is missing, like that there is nothing there. It's a 0 number of particles and so on. And this acts as a 0 under system composition, because if I composite system A with nothing, I still get A. So what you basically can show is that the entropy of nothing is equal to the entropy of nothing composed to nothing, which means it's twice the entropy of nothing, therefore the entropy has to be 0. Or another way to say it is that no state can describe a system more accurately than stating the system is not there, if you consider this entropy as sort of being related to information, because it's the number of evolution. The fewer evolution you get, the better. And again, this is going to be equivalent to the third law. This is going to be working the same. So takeaways from this is that thermodynamics can be recovered as describing an equilibrium of system and parts. And so the notion of process entropy maps to the thermodynamic equilibrium in a very natural way. And the thermodynamic equilibrium is basically an equilibrium at all scale. It's something that already people discuss. I should put citation. I was lazy and I didn't find it. And again, we have not mentioned about uncertainty, disorder, statistical distribution, nothing. This is just the count of evolution and types of equilibria, and we have not discussed the type of system. So in principle, this could be written as down as a whole theory that is independent by a lot of things, and we still need to do it. At some point, we're going to get around to it. But the ideas are there, and we need the ideas because, again, when you're doing reverse physics, you can't really deconstruct one theory without thinking about all the others. There are pieces that go there. Now, I'm basically done. One of the things that I want to show you is the sort of ideas that already links classical mechanics, quantum mechanics, and thermodynamics, statistical mechanics together. And it's this notion of having a classical uncertainty principle. We saw that a lot of classical mechanics could be recovered with ideas that have to do about information entropy, and so on. And what you find is that, in principle, classical mechanics violates the third law because it has no lower bound on the entropy. If you think of entropy as a volume of phase space, we can shrink that volume all the way to zero. And the logarithm of zero is minus infinity. So we can make that volume as small as we want, as small as we want. And at some point, we are going to cross over and go to negative entropy, which of course does not make sense. So the idea is what happens if we take classical mechanics and impose the third law, impose that there is a minimum of entropy. And so let W0 be the volume of phase space over which a uniform distribution has that zero entropy. At some point, we take the volume, we shrink, we have a uniform distribution. At some point, we are going to hit the zero entropy. So let's say that volume is W0. If you now try to find what is the uncertainty allowed by an entropy given by that same volume, you find that the distribution that minimizes the uncertainty given that same entropy is a Gaussian, and the product of the uncertainty of Q and P is greater or equal to W0 over 2 pi E, where this equality is saturated. It's exactly unequal when you have independent Gaussian for position momentum. So in the graph here, we basically say imagine this is the space of all distribution that you put in phase space. We order them on this axis by entropy. So a distribution that is here is higher entropy and here is lower entropy. And this is the zero. So we are excluding all the distribution that are here. We have on this axis the product of the uncertainty. So there are going to be things that have low uncertainty, higher uncertainty, and things that are low uncertainty. And we have this exponential here, which corresponds, this region here that corresponds to the region of the Gaussian, where you have the minimum uncertainty, and the minimum uncertainty is going to increase in this way. And this is going to be the region of the classical distributions that are allowed. And you find that there is nothing here, something that is a lower uncertainty here doesn't exist. And the lowest uncertainty possible, of course, is taken when we are here at zero. And so the point is that a lower bound on entropy gives us a lower bound on the uncertainty, even in classical mechanics. So we don't need the full quantum theory to derive an uncertainty principle. We just need to assume a lower bound on the entropy. So this is kind of the way that we think about it, is that we have these third laws of thermodynamics that tell us that there is the entropy is zero. And we said this principle of maximum description, that no state can describe a system more accurately than stating that the system is not there in the first place. So it's sort of half a joke, half serious. But these two things are for us interchangeable. This gives this to this, and this leads to this. And we saw that this gives us a lower bound on entropy. that in classical mechanics, we have to add to get an uncertainty principle. But in quantum mechanics have both, this implies a lower bound of entropy because the entropy of pure state is actually zero. You can't have a statistical mixture in quantum mechanics that is lower than zero. And so quantum mechanics gives us both the lower bound of entropy and the uncertainty principle. So if we can really understand the uncertainty principle, it's not a feature of quantum mechanics per se, but as a feature of the lower entropy bound. And one of the things that we would like to show, and we'll talk about it extensively tomorrow in the region of quantum, is can we actually say that quantum mechanics is just this? That we have a lower bound on the entropy, all the distributions that have more refined entropy are not accessible. Then we can't create an ensemble for those distributions, so they cannot be studied reliably. And so the only ensembles that are accessible to us are the one at that resolution, at that zero entropy. And therefore, we can't take a distribution and chop it up into points and map the points. We can't map the parts. We can only map this ensemble as a whole. And so the idea is that enough for just giving the whole quantum mechanics, or there are other things that we need to put or not? And this is, for us, sort of the part of the research that we've done. So to wrap it up, we think we have the basic concept, and sort of we did the first part of reverse physics and thermodynamics. We think we have identified the pieces. We just need to make the work. And we think that basic concepts like entropy and equilibria are linked to fundamental requirements for defining physical systems. And so, in a sense, thermodynamics, or at least those parts of thermodynamics that talk about a notion of entropy and equilibrium, are actually more fundamental than people think. One other thing that goes with that reasoning is that the geometric structure of both classical and quantum mechanics are exactly the structure that you need to be able to define entropy of ensembles. Because if you think about it, we saw in classical mechanics is all about conservation of these areas and so on. And those are exactly the type of things that you need to define the entropy in a coherent invariant way. So the geometric structure of classical mechanics is exactly the entropic structure. And the same thing can be shown in quantum mechanics. If I tell you what the entropy of all the different mixtures are, you can recover the inner product. You can recover the structure of the geometric structure of quantum mechanics. Therefore, there is a sense in which all the geometric structures that we have in physics are really entropic structures, so that entropy is really a more fundamental quantity that if you take out, you're basically taking out everything. And so then thermodynamics itself kind of extends this concept to the notion of equilibria among subsystems, such that the thermodynamic equilibria is a bigger requirement than just an equilibrium, because you're saying that all the parts are in equilibrium such that you can take them apart, and that's fine. You have an independent system. While in general, if you take them apart, taking them apart would also mean getting rid of the color relations, and that getting rid of the color relation would be another thermodynamic process of going to some other type of equilibrium. And one of the things that I want to stress is that the idea are general and could explain why techniques from thermodynamics have found place in ecology, economics, and everything. And this is something, the type of things that I'd like to have, definitions that are very general, out of nowhere, they recover things that you wouldn't expect. And again, we think that these are good foundational ideas, but we still need to put them together and do the due diligence, make sure that the math works in a more deep way, in the same way that we did for classical mechanics. So I think that's what I had. So we can open up for questions. And at this point, I don't know, we can just ask the questions directly, because there are not many people. So if you just want to raise your hand and ask questions, then also it's fine.
So hello. So I have one question.
Mhm.
In any dissipative scenario, we will have that the system which is dissipating energy will have a decrease in the entropy, but the whole system as a whole, with the environment with it, the entropy will be increasing, right?
Right. So there is So we still haven't figured out exactly the difference of what happens for dynamical systems and so the notion of dissipative things that you have in dynamical system and in thermodynamic system. We haven't done the due diligence to see how things map. Whether the total entropy is conserved or not, it's essentially a question of assumption. So in thermodynamics, you always kind of assume that the reservoir and the environment plus the system are, let's say, independent from everything else, such that the reservoir and the system itself are in equilibrium. And
Yes.
if you make those assumptions, then the entropy is conserved because that whole thing is already in equilibrium kind of stays. It, it's one of the issues here is always in physics is where do you make the cut of the system that you're considering? And
Yes, exactly.
right, and that's kind of I don't know how to say it's never objective to me in the sense that it depends what system you're considering. So if you're
Okay.
only considering the system by itself, then the entropy is going to decrease and increase depending on what the system is doing. And you can always assume, at least mathematically, that you can always increase the size of the system to have something that it's closed. Like it's a trick that you do um, in probability theory. In probability theory, a lot of the proofs, so you have a set of variables that are correlated, they are a mess. And then what you do is say, I can always add other variables and then make the whole thing uncorrelated, solve the problem, and then do the projection on the margin. Right? And
Yeah.
this is something that you can always do in classical mechanics and in quantum mechanics. In quantum mechanics, even if you have a mixture, statistical mixture, you can always say, oh, this statistical mixture is part of a pure state that is bigger. And so since you can always do these things mathematically, it's kind of like physically you're always assumed to say that you're always okay to say my system is coupled to a bigger system and the whole thing is isolated.
Yeah. Okay.
But I don't know. So since it's can I say, since it's a mathematical trick, I don't know whether you should really interpret it as, oh, yes, it's always that the case, or I can always construct a model in which that's the case, right? So the interpretation
Yeah.
of this is fuzzy to me.
Okay. Thank you.
I can comment. I mean, I think if you think of a dissipative system like a damped harmonic oscillator, um, we don't even consider we don't consider the dynamic evolution of the environment. Right? Yeah. So it's sort of
Yeah.
outside of what you would typically do in a physics problem. But yeah,
Yeah.
thinking more carefully about these things is certainly part of what we want to do.
Yeah. One more question. When you were speaking about the when we have a state space and we had some evolve of the state from one state to another, we had a merging of the states and splitting of the states, right?
Mhm.
So so the transformation from one state to another state is done by a Hamiltonian that depends on time or doesn't depend on time. Because if I remember correctly, when the Hamiltonian doesn't explicitly depend on time, then according to Liouville theorem, there is no merging of states, that no trajectories can intersect or at any time, right?
Yeah. That's always true. Even in time evolution, if you consider the flow, through the region, you're always flowing, you're always incompressible.
Yeah.
when you have Hamiltonian mechanics, you are only considering a dynamics that is deterministic and reversible. So when you the dynamics where things merge and split would be more complicated. Would be things that you would study with actual statistical mechanics that does not have a Hamiltonian underneath.
Okay. Okay.
It would be something like like a stochastic process, essentially.
Yes, exactly. Yes, yes, yes.
Yeah. And when you have a stochastic process, anything goes, essentially. And so what I showed before, if I can get to the, let's see if I have this. Can I quickly switch? Okay. I have not done this format, so I'm trying to let myself use this. Exchanging slide quickly is not convenient, but I should be able to do this conveniently. So this idea that a process is a set of possible evolution, that's exactly what you do in stochastic systems. The stochastic system, the set of points are all the possible evolution that are assumed to be continuous. And you put a probability distribution on that. That's kind of what you're doing. What we're doing here is slightly different because we're not really technically putting a probability distribution on that space. We are putting a measure that is not necessarily bound, which counts the state, but the mathematical instruction is very similar, and then we can recover the one from what's it called, from the stochastic process by basically putting a constraint. But once you put a constraint, that constraint is gonna essentially define a subset of evolutions, and on that you're gonna sort of get a probability distribution. So a lot of the math that we have is actually hopefully inherited from stochastic processes. And the idea is that something like Hamiltonian mechanics would be a special case, would be a special case where you have perfect correlations between all states at all points, and you can only go transition one to one.
Yeah. Okay. Thank you.
So I can comment on that. So, I mean, I think deterministic processes play a special role in science, not necessarily the world, but in science, because in science we're interested in trying to make predictions. So we're interested in trying to identify processes that are deterministic or approximately deterministic so that we can use them to make predictions about the future given observations in the present.
Right. So the more the process is deterministic or reversible, so the more that you have constraints on these evolutions, the more you can say. Like you can imagine a system where it can go from any state to any state at any time. So you have all the possible permutation, all our possible evolution. What can you say about this system? Nothing. It's noise, right? And
Yeah.
and so the idea is that you try to find the things that sort of have correlations, and then you can say something.
Yeah.
That there is like one of the things that I wish there was, but I don't know if it exists. I don't know if it's possible. If it would be like there would be some kind of theorem or whatever that given a process with a set of evolution, you can sort of decouple the part that is that you can say something about from the part that is pure noise, right? Some kind of like canonical decomposition. I don't know if such things exist. If there exist, then you would be able to say something like. I don't know that in a classical system you always have some kind of component that it's deterministic and reversible, that it's let's say Hamiltonian, but then you have some part that it's the sort of the Macaulay part that you can superimpose, and maybe there are different parts that sort of act on the randomness in different ways. So it'd be nice to know if such a thing exists in general. I know that some. I've seen some vague thing that were kind of pointing to this in the literature, but never something done generally full. So I don't know if it's possible.
Okay.
I have a question, but I don't know if my audio is working. Can you hear me?
It's a little bit garbled.
Yeah, it's bad. I don't know. Or it's the same.
I can't understand it. Want to type it in the chat, maybe?
Yeah, you can type. Yeah.
Oh, yes.
He's rejoining. We're joining on another device.
Yes. True.
Connection problems. Isn't your approach to thermodynamics almost to connecting to the very bottom? Bottom of what? Like essentially from mathematical physics. I'm not understanding the question. I guess this would be a question that it's easier to ask in words than writing it down.
And physical methods. Which are already connected.
Your reverse physical pressure and the physical mathematical pressure are already correct. Part of it, yes. Parts of it, no. I mean, so there are different pieces that we are missing on each side to be able to make a full connection. Let's see. Right now, we have a gap in between the mathematical physics because we have a topology, which is very low level. And then we are developing a theory of ensemble, which is much higher level. And this part that we talk about in thermodynamics kind of sits in between, right? Because this is sort of the idea of we are trying to develop some kind of a theory that tells me what the ensembles are, why do we care about ensembles in equilibrium, why do we have an entropy, what is it, and so on. I currently don't have that in the physical mathematics. As you see on Thursday, the thing that we're working on right now is just assuming that we have ensembles and we're assuming that we have entropy and build things on top. And we're doing that because that thing does so much and we want to get that done before anything else and then we can work as sort of a layer in between. It's not clear to me exactly what the right even mathematics is for this. And but I do want to get the concept. So this idea of putting a measure on the count of states, to me, it's more what I'm trying to figure out right now. It's more, and I talked about right now. It's the physical justification, right? So I can only do physical mathematics if I have a physical justification for the definitions. I can't even start doing physical mathematics if I don't know that I have concepts that are going to actually work at the physical level. It's just going to be a waste of time, right? So if I had a concept that kind of something like disorder or stuff like that, right? I can't create even if I try to create a mathematical sound way to talk about disorder and so on. it wouldn't be the right concept. So there is a saying that mathematicians say that you should never prove a theorem until you know it's true. And kind of here is the same way. Like you only construct, like the physical mathematical approach costs a lot of time. It's a lot more involved. It's a pain. And so you only do for things that, this is definitely gonna work and it's gonna give you the right thing. So you do it at the end. But does that answer your question at all, or okay? Yes, he typed yes. Good enough for government work. Yes. So we have 20 minutes. So if there's anybody that wants to ask a question about anything about the project, please go ahead. If there are no questions in a minute, we are probably going to close. Okay, shall we close then? Closing one, closing two, closing three. Okay. Thank you all for joining and for your attention, and we'll start again tomorrow at the same time.
Thank you.
Thank you.
Bye.